same sheet from last time, at least at the start, on the related rate stuff. So let's see, we talked about the melting snowball. So let's look at the next one. All right, so let's see what we got. We've got Omar flies a kite. 150 meters high. The third page, the number 2, yeah. All right, so here's the situation. We've got a dude and a kite. It's a pretty sweet kite, right? Okay, and the wind is blowing at this direction at 5 meters per second, and he wants to keep the thing at a constant 150 meter altitude. So obviously, the distance between him and the kite is going to be more than 150 meters, right? Because as the wind blows it away from him, he's going to have to let out string, right, in order for it to keep a constant altitude. Okay, so the question is, at the moment when there's 250 meters of string out, how fast is the string going out? Okay. All right. So does that the question makes sense? Yeah. Okay. So we've got a couple things that we need to determine here. The first is, let's call this distance x, the distance that um, the kite is away from him along the horizontal, and let's call this distance z for the actual string length. Okay, so what we're trying to find here is something about the rate at which z is changing, right? Okay, so that means that we need an equation that relates stuff that we have together here. Okay, and there's maybe two options for it. Uh, what are maybe some options for things that relate all of these variables together? Pythagoras' theorem is certainly one, right? Because we've got a right triangle, and we know one of the three sides, okay, but we can still write down Pythagoras' theorem. The other one that we could use actually would be cosine, right? Because the cosine of this angle would be x over z. But I agree that Pythagoras' theorem is probably going to be the easier move here. Okay, so what would that say? It would say that x squared plus 150 squared equals z squared. Okay. And then we need to start taking derivatives of this, right? Because what are we interested in finding? We want to find dz dt given what's dx dt? Well, how fast is the kite flying away from us? Yeah, the 5 meters per second, right? Just that it's getting blown by the wind. Okay, great. Um, so I can't plug the 5 into anything yet because, well, right now my equation has no rates in it. It's just a static thing. Okay. So that said, what is the derivative of this equation? All right, so 2x dx dt plus 0 equals 2z dz dt. Of course, the 0 because the 150 is constant. Okay, so we're trying to find dz dt, right? Do we know dz dt? No, and that's okay because that's what we're trying to find. Do we know z at the moment in question? Yes, and what is it? 250. That's how much string he's let out. Okay. Do we know x at the moment in question? No. Do we know dx dt at the moment in question? Yeah, that's the 5. Okay. So the first thing we need to do is, so we know that z is 250, dx dt is 5, but we don't know x. Okay. And so to find x, what we actually just do is we go back to Pythagoras' theorem, because at that moment, we do know this, right? At the instant in time where there's 250 feet of string out, or meters, excuse me, we know it's 150 meters above the ground. We know he's let out 250, and we know this is a right triangle. Yes? Okay. So what does Pythagoras' theorem say that x is, in this case? It's going to be 200, okay? Um, Now, if you don't recognize that quickly, then just solve x squared plus 150 squared equals 250 squared. But if you think about this for a moment, this is actually a 3, 4, 5 right triangle, right? So if you divide everything by 50, then um, you've got 3 something 5. Well, what's 3 squared plus 4 squared? 5 squared. So that means that this one would be 4 times 50, right? Yeah, so sometimes you get lucky with the numbers. And yeah, all right, so we got what, 200 meters? And so now we just need to substitute all that stuff into here. Okay, and so that gets us what, 2 times 200 times 5, which was dx dt, equals 2 times, what was z, 250 times dz dt. Okay, so then we just have to divide everything out. Okay, so the 2's cancel, and 200 over 250 is 4 over 5. So this would be 4/5 times 5, or 4 meters per second. Hopefully I did the arithmetic correctly. So look good? Does 4 meters a second sound reasonable? Yeah. Um, why does it make sense that it's not 5 meters a second? Huh? Yeah, it's at an angle, right? It would be going 5 meters per second if he was at 150 meters above the ground and the kite was just going straight away from him. Okay. And it certainly makes sense that it's positive, right? Now, what do we think is true? Is it increasing, like this 4 meters per second? So if I did this when he'd let out 500 meters of string, would it be more or less than 4? It'd probably be more, and why? Yeah, exactly. So um, if let's say that he had like 10 kilometers worth of string, right? If it's 10 kilometers worth of string, does that 150-meter altitude really make that much of a difference? No. So as the amount of string goes to infinity, then this rate would approach 5, which is the wind speed. So it would asymptotically approach it from below. Okay, um, which is just kind of fun. Okay. Um, all right. So let's think about the procedure here, right? What's basically the very first thing you want to do for almost any one of these problems? Is draw a freaking picture. Okay, it doesn't have to be a great picture, but it just needs to be some sort of schematic that helps you relate all the variables together. Okay, that will help you determine what your key equation is. Okay, which is the equation, or sometimes actually there's more than one, that relates all of the different variables together. Once you've got that, then you can start differentiating, plugging in, and so on. Okay. Um, but don't differentiate until after you've got the key equation. Okay. All right. So let's look at another one. Any questions on this one? No. Okay. So there's a rock along a shore. Okay. So let's put the rock here, and 100 yards east of it is a lighthouse. This is my cheesy lighthouse. And then there's this bougie hotel over there. Okay, and the distances here are 100 yards, 173 yards. Okay, and great. Okay, so this lighthouse, well, what do lighthouses do? Yeah, and so they go kind of in a circular pattern, and the assumption here is that the beam of light goes around twice per minute. Okay, so let me draw sort of what an arbitrary beam would look like. Okay, and it's going to make some sort of angle here to the horizontal. Okay. Um, so what we want to know is how fast is the beam moving when it hits the hotel. Okay, so what I mean is, like, the beam of light is there's gonna be a bright spot, and if we follow that bright spot as it moves, it's going to appear to move at some rate. We want to know what that rate is. Okay. Um, okay, does that make sense? Now, the other thing that we can say here is, well, how fast does the light actually emanate from the lighthouse? Yeah, very, very fast. Okay, so much faster than the sizes of this problem that we can basically treat light as if it moves instantly. Okay. Um, I'm sure Dr. Brown would get irritated with us over this problem, but that's okay. Okay, so if the thing rotates at 2 revolutions per minute, then what is d theta dt? Okay, so theta is this angle that we're going to measure from the lighthouse to, well, wherever it hits. What is d theta dt? Well, let's think about it. What units does this need to be in? Well, it's an angle, so what units do we use for angles? Degrees or radians? Okay, which one are we going to use? We're going to use radians. Okay, why? For calculus purposes, yes. Okay, So what's the derivative of sine of theta? Assuming that theta is measured in radians, it's cosine theta. If you measure it in degrees, then you have to do like a pi over 180 bunch of garbage. Okay, so the same reason that we measure, that we do logarithms, that we prefer the natural ones because they make the calculus easier. Same reason for the trig functions, we actually want to work in radians and not in degrees. Of course, we could always convert them, so it's not the end of the world, but um, we'll work in radians. Okay, so how many radians are there in a full circle? Well, how many degrees are there? 360, right? How many radians is that? 2 pi, okay? So if this thing rotates at twice per minute, how many radians is it going through in a minute? 4 pi, okay? So 4 pi radians per minute. Okay. Is that okay? Okay. Now, let's say that we were given information in degrees per unit time. In order to do calculus, we'd need to convert that into radians. And of course, what's the conversion? If 360 degrees is 2 pi radians, then pi radians is 180 degrees, and there's your conversion factor. You just either multiply or divide by pi over 180, depending on which direction you're trying to do the conversion. Yeah, and you guys all did that in high school, right? Yeah. I feel like we're a little light today, given that, what are you guys doing this later today? Your next, celebration of learning. Yeah, it's not an exam, it's not a test, it's not a assessment, it's a celebration of all the wonderful things you've all learned. Well, I've already printed them, but you can cross it out and write celebration of learning. Okay. Okay. Now that we've sorted that out, we need an equation that's going to relate the quantities in question, okay? And so let me think of the distance that the beam has gone along the horizon or along the shore. Let me think of that as x. And we'll be interested in it at the moment when x hits 173. Okay, but it's not going to be that distance always. Okay, is that all right? Okay, so I need an equation that's going to relate 100, x, and theta. What's going to be the droid we want? We could use Pythagoras' theorem, but what would be better is to use a trig function, okay? And so the reason that we don't want to use Pythagoras' theorem in this case is we have information about that angle, right? Does an angle appear in Pythagoras' theorem? No. So we'd be like leaving a card on the table. Okay. The other reason is that we don't know anything about the distance between the lighthouse and stuff, right? I mean, it would vary. Okay, so Pythagoras' theorem is out here. Which trig function do I need? I want tangent, and why is tangent the one? Yeah, because it's opposite, which I've called x here, and adjacent, which is 100, okay? Both of which we have some information about. So I want to use here tangent of theta is 100 over x. And that's my key equation. Yes. Sine over cosine. No, it would be, um, so sine can't be 100. And think about why. What's the biggest sine can ever be? 1. So, right, that only works assuming that the hypotenuse is 1 unit. If it's not, you have to divide both of them by it. So, yeah. I'm sorry, I wrote this upside down. Yeah, yeah, there we go. Yeah, so opposite over hypotenuse. I mean, over adjacent, right? For tangent. Okay, that'll make the next step a little easier. Right? Okay, so Gucci. All right, so now I need to take the derivative of this thing. Okay, so what's the derivative of secant theta? Sorry, tangent theta. Blah, blah, blah. Secant squared of theta times, no, d something, d something, d theta dt. Why do we have to have that? Because theta depends on t. This is the chain rule, right? Okay, what about the right-hand side? Don't have to do the quotient rule here. And the reason is one of the terms is just a constant. So can I think of x over 100 as just 1 over 100 times x? Well, 1 over 100 is a constant, so I can just kind of keep up with it. And what's the derivative of x? Dx dt, right? Because we have to do all of this implicitly. Okay, so that Gucci? Yeah? Okay, so if you did use the quotient rule, well, let's just do that, right? So let's just come over here and say, all right, it'd be low d high minus high d low all over low squared. Right? So, yeah, you could use the quotient rule. I wouldn't. Not necessary here, but yeah. Okay, so now let's see, what else do we need to do? We need to start plugging stuff in. Okay. Do we know d theta dt? 4 pi, right? Do we know dx dt? No, and that's okay because that's what we're trying to solve for. Do we know secant squared of theta? Well, not quite, but can we figure it out? Yes, maybe. Okay. And the reason that we'll be able to figure it out here is because at what moment in time are we interested in what X is doing? We're interested when the beam hits the hotel. Okay. So at that moment in time, we have 100 and 173 here, and this is our angle. Okay. All right. So we need to know the secant of theta at that moment in time. What do we know? We know the tangent of theta. Okay. And this 173 was chosen not arbitrarily, because this just so happens to be the square root of 3. Okay. Because 173 divided by 100 would be 1.73. That's basically the square root of 3. Yeah. Okay. So that was picked deliberately because then what angle do I know that theta actually is? That unit circle. Okay. Tangent of what angle equals root 3? Pi over 3, or 60 degrees. Okay. So I know that the angle at the moment in time is basically a pi over 3 angle. Okay. Now, does 60 degrees seem reasonable just from a eyeballing it standpoint, because I've got 100 and 173 there? It's definitely more than 45, right? Because if that 173 were 100, then it'd be 45 on the nose. Okay, so does that seem reasonable, right? Okay. Um, okay, So what I need to know then is what's the secant of that angle? Well, what is secant? It's 1 over cosine, right? Okay, so if I want to know that, what is cosine of pi thirds or 60 degrees? 1/2. So 1 over that is 2, okay? And then what do I actually need to do to that? So I get 4. Okay, so what I claim then is that at the instant in time that we're working with, secant squared of theta is 4. Okay, so let's go back through why. What angle did we just figure out theta was at the moment in time we care about? 60 degrees or pi thirds radians. What is the secant squared of that number? Well, secant is 1 over cosine, right? What's cosine of 60? 1/2, so therefore the secant is 2, the reciprocal. And do I have secant? No, I have secant squared, so 2 squared is 4. Okay, so what I get is 4 times d theta dt, which happens to be 4 pi, okay, is equal to 100, or 1 over 100, times dx dt. All right, so what's dx dt? It'd be 100 times 4 times 4 pi. And what would the units of this be, by the way? Yards per minute. Okay, does that make sense? Yeah, 1 second. The 4, which 4? This 4? Yeah, okay. So there. Okay, so we deduced that at the moment in question, the triangle we were looking at had a base of 100, height of 173, and unknown hypotenuse. Okay. But we knew that at that moment, the angle is 60 degrees. Okay. Now, I need to plug that into secant squared of theta. So I need to determine the secant of that angle, right? The angle is 60 degrees, right? So what is cosine of 60 degrees? Well, what is secant? Secant is the reciprocal of cosine, right? So I know my angle is 60 degrees. What is cosine of 60 degrees? 1/2. All right, so if secant's the reciprocal of that, what's secant of the angle? 2, okay? But I didn't have secant in my equation, I had secant squared. So 2 squared is 4. Yeah? Okay, good? Yeah, so the number was cherry picked in order to make this number nice. Okay, let me just actually mention, by the way, what would have happened if you didn't recognize that the numbers here were picked so as to make the tangent equal to √3, make it one of the special angles. Okay, what would I have done instead? Like, let's say that this came out to like 1.5 or something. I don't know what the hell it is. Well, if I know that tangent of theta is equal to some number, how can I solve this equation for theta? Is there a way to sort of undo tangent? And what is it? No. Nope. Arctangent. Right? Remember the inverse trig functions? Yeah. Great. All right, so what I would do is I would take arctangent of 173 over 100 and see what I get. Okay, now, when you do that, you do have to be a little bit careful because, in fact, let me just pop Wolfram Alpha open. Oh, not Canvas. I wanted this one. Where is my English keyboard? Well, it's because it's in symbol mode, but what I'm looking for is a freaking backspace. Okay, let's just clear everything then. There we go. All right. So what I want to do is arctangent of, what was it, 1.73, right? Oh, hang on. Apparently there's been a lot of chit-chat about Edgerome lately. Edgerome. There's been a lot of yicking and yakking about it. Okay, so what we get, right, is the measure in radians and the measure in degrees, and whether we get 59.97, which I call just flat out 60. Okay, yeah. Or a calculator? You don't. Um, no. I'll cook the numbers or tell you. By the way, yeah. Um, yes. Okay. So fair point. You would not be able to. So like, let's say that I change this from 1.73 to like 1.5. Yeah. No, why? Why? Okay. So let's just say 1.5. Okay. Then it's not a special angle. That's one that we learned off the unit circle. There's no way around figuring it out um, numerically without a calculator. Well, or how would you have done this back in the day before there were calculators? Hmm? Okay, so, you know, unsolvable. No. Um, what you would have done is you would have had other tools at your disposal. Okay, so for example, you would have had a slide rule perhaps, or a book of tables that had trig values for every, minute or of arc, perhaps, and you would have to approximate accordingly. So yeah, it was actually possible to do this pre-calculators because, well, all right, so all this trig stuff, what do you think it's useful for? Huh? Triangles, yeah, which means like if you're surveying or, right, which ultimately comes down to taxes, right? Because if you want to survey the size of a piece of land, then that tells you how much you should tax it. Okay. Why do you think the Egyptians started figuring this stuff out? Well, that and pyramid building, but you know, yeah. Yeah, it's really important, right? Okay, so yeah, but it's also really important if you want to, oh, I don't know, sail the world. Uh, no, hadn't quite been discovered just yet. Okay, huh? Well, yeah, there were stars, right? And so, yeah, trigonometry, applied trigonometry, the fun case is the spherical versions, which is the math behind celestial navigation. And hopefully, a certain professor will be teaching a topics course on that in a few semesters. Yeah, wouldn't that be cool? Math. Yeah. Huh? Oh, I don't know. Calc 2 would be good, yeah. But yeah, you'd have a sextant, you'd have a slide rule, and you'd have a book of tables, and that's all you need. Huh? You, yeah, okay, Moana could just do her thing, right? Which actually does, I mean, this is a very interesting question. How the heck did the people that, the indigenous people of Hawaii, how did they get there? That's a long way away from other stuff, right? Yeah. Well, probably. They didn't probably know they were aiming for that, but like, all right. So, good. So let me go to, let's go back to the sheet. Um, and I need to look at what we're going to do next. No, Lord, no. I wouldn't do that to you guys. That would have been cruel. Oops. I want this one. Okay, so let's do this one. So let's suppose that you've got a dude who's 6 feet tall and a lamppost is 15 feet tall. Okay, so what's going to happen, obviously, as the dude walks? If he walks away from the lamppost, what's going to happen to his shadow? It's going to get longer, right? And what we want to understand is how fast does the tip of the shadow actually go? Okay. All right. So let me call this point here um, that it's some distance away from the origin. And I'll put the lamppost at the origin or, um, and what's the height of the lamppost? It's 15 feet. He's 6 feet. Okay. And then the other thing I'm going to say is that he is X units away from the um, uh, away from the lamppost. Okay. Now, do you see why I used X and Y separately here? Right, because his distance away from the lamppost. Well, okay, we actually, why don't we do this? Why don't we change it to that? Okay. And why does that maybe make a little bit more sense? Because what do we want to know? We want to know how fast the length of the shadow is growing. But where does the shadow start? Where the person is, not where the lamppost is. Okay, so that actually probably makes it more sense to label Y that way. Okay, so he's X feet away from the lamppost, and then the shadow is some extra number of feet beyond him. Okay, does that make sense? All right, so we want to find dy dt basically. And what do we know here? How fast is the dude walking? Okay, and that has to be given, and we'll say it's 2 feet per second. Okay, and we want to find dy dt. Okay, all right, so what key equation do we think we might want to use here? Well, we've got a right triangle. Actually, we have two right triangles, right? So Pythagoras' theorem is certainly an option, okay? But there's another way. And so in order to see that other way, let me actually draw do you guys see both of those triangles in my bigger figure? Yeah, and what's true about those triangles? They're similar. Yes, which means that if I look at the ratio of corresponding parts, I'm going to get the same values. Okay, because now how do I know that they're similar, by the way? They share this angle in common, and this angle is right for both of them, and so therefore, what's this angle up here? The same value, okay? So if all three of their angles are the same, then as the corresponding ones in the other triangle, that means they're similar, which means their corresponding parts are proportional. Okay, good? Okay, so what proportion can I write down here? Well, a bunch of them, but let me do it this way. Let me say as x plus y is to 15, so too is y to 6. Right? So as base is to height, so too is base to height. Yeah? Okay. Now I could have written a whole bunch of other versions of that, but this one is maybe the easiest to use because I put the variables on the top for convenience. Okay, does that make sense? All right, so what do I need to do to this? Next. Huh? Yeah, we need to do some calculus. Let's take the derivative. Okay, so the derivative of this equation is dx dt plus dy dt all over 15 equals dy dt all over 6. You could, because otherwise you're going to have to do it now, right? And so what am I trying to solve for here? I'm trying to solve for dy dt. Because I'm lazy. I get that. Yeah. And so what do I need to do to get dy dt by itself? Multiply by 10. And then at the moment of time that we're interested in, what was dx dt? Is 2, okay? So, yeah, 4/3 feet per second, okay? Does that number seem reasonable? You know? Okay, so now here's another question though. How fast is the tip of the shadow actually moving? Is it 4/3 or is it something different? It's something different because, so what we just found is the rate at which the length of the shadow is changing. But how fast is the tip of the shadow moving? It's faster, okay? And here's why. Where does the shadow start? Wherever the person is, who is also moving, right? So the rate at which the tip is moving is actually, we found 4/3 is the rate that y is changing. What's the rate that x was changing? 2. And so how fast is this tip moving? 2 plus 4/3, the sum of the two. Okay. Does that make sense? Because this is changing and the dude is also moving. Yeah. So it'd be kind of like me saying the following, right? If I can throw a ball at 2 feet per second. Well, what about if I'm already going 5 feet per second when I throw it? How fast is the thing going relative to a stationary observer? 7, right? So this is Galilean relativity, right? Which is fun, right? Yeah. Okay. All right. So I think that's pretty good for related rates. It will not be on the thing today because that would be cruel to make you guys do this already. So anyway, okay. So usual drill. I've got the folder in my bag. Grab the one with your name on it, and you're either going to do the ones that are circled or not the ones that are X'd as appropriate. Please work it out on separate paper. Don't try and squeeze everything on the sheet, and use as much space as you need to and so on, right? And then what do you do when you're done? Staple it after you remove the frillies, if they exist, and put it in the other folder outside the door, and get them done by 4 or 5 o'clock today, please. Good? All right. Have a good rest of your Monday.